AP statistics. So finishing up chapter 7 in section 7.3. In the last video, we looked at the sampling distribution of X bar and how we could calculate its center, we could calculate its spread, and then the shape, if the population was normal, is also normal. Well, this section adds a really key piece, and some people actually call this piece the fundamental theorem of statistics, kind of playing off that fundamental theorem of calculus if you're taking calculus. But this is a really, if nothing else, hopefully that just illustrates to you guys how important this is, and really just is why normal distributions are as important as they are. So the central limit theorem. Most population distributions are not normal. All right, that's just the reality of it. They're not normal. So here are approximate sampling distributions of X bar for samples of size 2 and samples of size 25 from 3 different populations. So here's our population distribution. So if we have a population distribution that is uniform like that, and they're not showing the sample data, but they're showing the sampling distribution of samples of size 2. If I get 2 individuals from that, we've kind of seen this before, where actually this is like when we do our dice. Remember how they kind of lump up like this? It doesn't match that uniform distribution. Numbers towards the middle are a little more likely. Well, it's still a kind of a weird shape, but we start to see that lump happen. Well, if we take it up to sample size 25, all of a sudden it's all lumped up near the middle, but it starts to kind of have that shape, right? That maybe normal shape. If our parent population is skewed and we start to do a sample of size 2, it's still skewed, but it's kind of a little bit more nicely curved out. And so the bigger that sample gets, we see that we end up closer to that bell shape, maybe that normal distribution. This is a really weird population where we have really low numbers and really high numbers. And so our distribution, I've seen actually like AP question like this before where it says, what would this distribution look like? If we take samples of size 2, we're either going to get like 2 low, 2 high, or 1 low and 1 high, which end up giving us these 3 peaks, which is kind of weird. But if we take 25, we don't end up having a whole bunch of peaks. We just end up with this kind of nice curve again. And so what we see is that as we increase that sample size, it smooths out into a normal curve. And this is the sampling distribution. And so this is what's so important about this, is that the larger the sample size we get, it's going to end up approaching an approximately normal sampling distribution, regardless of the population size. So draw an SRS of size n from any population with mean mu and finite standard deviation sigma. The central limit theorem says, and we can abbreviate this CLT, that's commonly used, says that when n is large, the sampling distribution of the sample mean X bar is approximately normal. So the larger we get, it's going to approach an approximately normal sampling distribution. It doesn't have to be a normal population. Normal population, it works even if with tiny samples, samples of size 2, samples of size 5. But if we get big enough samples, we end up following a normal distribution for our sampling distribution. So the shape, if the population distribution is normal, the sampling distribution of X bar will also be normal no matter what the sample size is. If the population distribution is not normal, the sampling distribution will be approximately normal when the sample size is large. That's technically the central limit theorem just says this. Our book gives this additional guide. If the sample size is at least 30 in most cases. If the population is extremely weird with outliers and things like that, you might even want a little beyond 30, but in the vast majority of cases, 30 is good. Even 10 to 15 is enough if your population's at least somewhat symmetric to begin with. If the sample size is small and the population distribution is not normal, the sampling distribution of X will retain some of the characteristics of its original population. So if the population starts skewed with a small sample size, it's probably still going to be skewed. So that's a big theorem to add to things. It's kind of what makes that normal distribution so neat and so useful, is that even when our population's not, our sampling distribution will be. So, example problem, Keith is the manager of an auto care center. Based on service records from the past year, the time in hours that a technician requires to complete a standard oil change and inspection follows a right skewed distribution, so not normal, with a mean of 30 and a standard deviation of 20. So the mean is the average of 30 minutes. Sometimes it takes a lot longer than that, right? That right skew. And then like the standard deviation of 20 gets us down to 10. Like you can't only go so far to the left. An oil change can't go below, definitely 0, but even still like a number higher than that. There's some minimum amount of time that it would potentially be done in. So that's the shape to start with. For a promotion, Keith randomly selects 40 current customers and offers them a free oil change and an inspection. If they redeem the offer during the next month, Keith budgets an average of 35 minutes per customer for a technician to complete the work. Will this be enough? All right, so that's going to be their average that we're going to be dealing with. So our average X bar is going to be matching the mean of the population, which was 30. Remember, the mean was 30, standard deviation was 20, the shape was skewed. The standard deviation, assuming that 40 is less than 10% of all current customers, which we'll assume that there are at least 400 customers if they're in business. And so we can use that standard deviation of 20 divided by square root of 40, and that's the standard deviation of the sample mean. All right, the average amount of time it will take. And so then the last thing is about the shape. Because that sample size is large, because 40 is greater than 30, the distribution of X bar is going to be approximately normal. So once you take the average of those 40 different customers coming in, on average, we expect that mean to be about 30, but maybe the average will be a little bit higher, a little bit lower because of whatever randomly 40 gets selected. So we ultimately want to know what's the probability that we go beyond that threshold right there, which was 35 minutes, exceeding 35 minutes. We're going to calculate that probability. And so a normal CDF calculation, we can do table, we can do this, but probably easiest way is this one down here. Lower bound, 35, upper bound, infinity, 1e99. Mean, 30, standard deviation, 3.16, and apparently there's about a 5% chance. So it seems like, 35 minutes should be enough, right? There's only about a 5% chance we would go beyond that. So there's only about a 5.68% probability that Keith hasn't budgeted enough time. Seems like we're probably good. 95-ish% chance that we're good. All right, so then part B, how much average time per customer should Keith budget if he wants to be 99% sure? Right there, we were about 95% sure that he doesn't go over budget. So here we were looking at the 99th percentile, right? Only a 1% chance we would go over budget, and so we want to figure out what that number is. Now we're going back, and again, the skills from this chapter have already been applied to find the shape, center, and spread. Now we're kind of going back to that chapter 2 calculation where we need to do an inverse norm. We need to do an inverse norm of the bottom 99% and figure out what that threshold is. And so, you could use the table, you could use z-scores and calculate a z-score and compute it out. The easiest way is to do the inverse norm of 0.99 with that mean and standard deviation, and it'll tell you 37.4, right, which is apparently 2.33 standard deviations above the mean. And so we need to budget an average of 37 minutes to be 99% sure that we budgeted enough time for that type of problem. So that is the central limit theorem. Really big idea, pretty simple idea really. Just the sample size is large. The sampling distribution of X bar will be approximately normal.